Can I ask everyone to get their seats? We're going to get started again. Hope everyone enjoyed their break, grabbed a coffee, connected with someone. So now we're going to move from core framework into how it's applied. So starting with production and then moving into research. So starting with our VP of AI Infra, Bill Jha, who's going to talk about how we deploy PyTorch at scale at Facebook. And then following that, there'll be a section by Jitendra Malik talking about how FAIR uses PyTorch in all of their research. So enjoy those talks, and we'll see you soon.
All right, good morning, everyone. I hope you enjoyed the deep dive PyTorch in the morning. My name is Bill Jha, and I lead AI Infra at Facebook. I guess I'm the guy who really care about production at scale at Facebook. To understand AI Infra at Facebook, let me first introduce our mission. So AI Infra mission at Facebook is to enable and scale AI systems and their uses by building cutting-edge machine learning infrastructure and platforms that empower Facebook to bring the world closer together. There are two keywords. The first keyword is enable. The second keyword is scale. So enable means we want to bring the AI research into production very, very quickly. The scale means once AI systems in the production, we can scale up to all the 2.2 billion users to use all these AI production systems. To understand the scale of AI system at Facebook, we understand Facebook has 2.2 billion monthly active users. And most of these monthly active users, they come to Facebook, use Facebook every single day. And our AI systems, every single day, they generate more than 300 trillion neural network-based prediction every single day. So that's 300,000 billion prediction every single day. In addition, our AI platforms, our AI frameworks, they're running more than 1 billion mobile phone devices, including iOS, including Android phones, high-end, mid-range, and low-end. And in addition, we're running a lot of experiments every single day at Facebook infrastructure. And I think we are running more than 1 or 2 million experiments every single day at AI infrastructure with massive scale. So we're running experiments. We're doing a lot of predictions. We really care about all the research work we can push into production very, very quickly. And once all these production systems in our infrastructure, we can run things very reliably, very efficiently, very performantly. So the three things we're doing right now at Facebook AI infrastructure. The middle one is developer platforms, which we understand that's Onyx, that's Cafe 2, and also the current PyTorch 1.0. And we allow all the AI researchers, AI developers to build models very, very quickly in a very flexible way. Then once we have models in place working very well, we push model into production, which on the left-hand side, we want to run AI as a service. All the data, all the features, and all the running, all the experiments, all the training work, eventually after get the model trained, we run the model into production. And many of the models we're running in production, and many of the models we're running experiments, they actually access tens of petabyte data, and also the model training sometimes running hours, days, or even weeks. So the scale we're talking about is massive. And after model got into production, running for inference work, we also have the foundation work on the right-hand side, which is bring all the massive model platform, software, into our data center, into our networking, into our customized AI hardwares. So the old process, well, that's pretty OK. What's the old process? So we do have the PyTorch, original PyTorch, which all the developers, all the researchers, they're building the AI prototyping, or the neural network prototyping. Working pretty OK. Very flexible, that's good. Then After the prototyping is done, we want to productionize it. Then we use Onyx to export the model into the middle format. After middle format, we get into Cafe 2. Then we deploy into production for training and for inference work. Well, this process is working pretty OK. And the Onyx in the middle, and much better than there's nothing in the middle. So these two systems are very disconnected. The Onyx in the middle is working pretty OK. But we do not like something in the middle. We just don't like it, because anything in the middle that disrupts the process. So what the thinking is, OK, how can we even reduce the middleman? How can we make these two different worlds, original PyTorch and Cafe 2, really merge together to create a very, very awesome end-to-end developer experience into the production experience? So that's our PyTorch 1.0. We all heard about this morning during the deep dive. So next, I want to introduce several different topics. Different speakers come here to talk about different topics about deploying PyTorch at production scale at Facebook. Different topics include scaling ML research, and neural machine translation, and Facebook conversational AI, and powering Oculus. That's all from research to production at massive scale. Without further ado, let me introduce Michael to talk about scaling ML research. Thank you.
Hello, everybody. So I will be telling you about scaling neural machine translation to very large settings. And we do this with our open source toolkit called FAIRSeq, which is a general purpose sequence-to-sequence learning toolkit that we use for research in machine translation, in document summarization, in story generation, dialogue, and the list goes on. And right after my talk, Juan will talk about a sister project called PyTorch Translate, which focuses on production aspects of bringing machine translation to all people at Facebook. So what is machine translation? So machine translation, simply put, is an AI application that allows you to understand content that is in a language that you do not understand. So the way it solves it, by simply translating it into a language that you understand. So why do we want to scale this? Well, until very recently, it took sometimes up to several weeks to train a neural machine translation system. And we need many translation systems to tackle all the languages that people speak. So the things we did was to first dramatically bring down training time. And then we used that capability to train on a lot more data to obtain much more accurate translation systems. And basically, these two ingredients were the basis for our recent submission to the WMT machine translation competition, which is the premier machine translation competition similar to ImageNet in computer vision. So in terms of scaling, we started off with an NMT system that usually trains in about 24 hours on 8-volt GPUs, which is already very fast. And then we introduced a couple of things. So first, we went to half-precision training, which gave a really nice performance improvement of about a factor of 3x. Then we played around with larger batching. So what we did is we moved the synchronization point after forward-backward into the future to process several batches at a time. And so the effective batch size increases, and the synchronization point is moved so you don't have to wait for stragglers. And that allowed us to increase the learning rate, because with large batch training you can do that, to further decrease training time. But there's another advantage of half-precision training, and that is that simply the neural network requires a lot less memory on your GPU, which doesn't have a lot of memory. So that allowed us to basically pack more data onto the GPU. And this is the red bar here, where we went from about 3,500 words per GPU to 5,000 words. And this all happened on a single machine. So we went from 24 hours to 5 hours here on a single machine. And then we scaled out to 120 GPUs, or 16 nodes, and arrived at about 32 minutes when we overlapped the backward pass with the gradient communication between the workers. So basically, when we compute a layer, we don't just wait until we backprop all the way to the input. We just start synchronizing as soon as gradients become available, which gets us to 32 minutes and about a 45x speed up. So this is training on labeled data. And now we can train on labeled data in half an hour, which is great. But we could also train on more data. The only problem is that the amount of data in translation is limited, so we don't have that much data that is available in a different language, particularly for low-resource languages. So what we did then is we started looking into semi-supervised training, so using unlabeled data. So unlabeled data in machine translation is simply data that is only available in a single language. So if you translate from English to German, so we wish to translate from English to German, there's this very well-known mechanism called back translation, which works as follows. So you take the labeled data, and you train a system that translates from German to English, so in the reverse direction that you actually would like to translate to, because we would like to translate from English to German. And you train an intermediate model. And then you use that model to translate a large German data set into English, for which you have no translations. So at that point, you actually have that large data set in German, also in English. And then what you do is you simply swap the direction again to the one you originally wanted to translate, which is from English to German. And you train basically a combined system with all that data. So that allowed us to scale from about 100 million labeled words to about just under 6 billion words, which is quite another notch up. And this showed in the terms of accuracy. So here we look at the accuracy in terms of the blue, which is basically a higher blue score means higher accuracy. And on the very right, we can see the performance with the labeled data only. And on the very left is the performance with the unlabeled data. So we get about a 4-point improvement. And to situate this, usually like an improvement about 1 point is seen as very significant. So here we have 4 points. And the middle bar here is a system that was regarded as the best system on this particular benchmark that we looked at that used proprietary data. Versus what we do here when we add monolingual data, we only use publicly available data. So this shows very nicely that it can do very well when you use large amounts of unlabeled data and do even better than proprietary systems. So this is the performance in terms of an automatic evaluation metric. But what do humans think about translations? Well, to answer that question, we submitted this system to the annual competition of machine translation, the WMT competition, where humans compare systems to each other. And amongst like a large cohort of systems, both systems that are available online as well as research systems, our entry sort of was ranked #1 by humans. OK, so all the things that I told you about are available in our open source project called FairSeek. Now I'll hand it over to Juan, who will talk about the sister project, PyTorch Translate, and he will tell you more about production aspects of machine translation.
Hello, everyone. My name is Juan, and I work on language and translation technologies at Facebook. I would like to thank the organizer for inviting me today. And thank you, Michael, for introducing me. So in his talk, Michael talked about how to scale neuro-machine translation research, especially on the training side. And now I'd like to talk a little bit about how to bring all these great improvements to people on Facebook. And I'll be talking about PyTorch Translate, which is our open source project. One of the main goals of PyTorch Translate is to showcase the path from research to production for a relatively complex natural language processing use case. I'll be talking about how people interact with machine translation on Facebook and other platforms. Then I'll explain why we use PyTorch to build our project. Maybe I don't need to convince you, but I'll explain it anyway. Then I'll explain a little bit the state of PyTorch Translate currently, what features are needed to serve all these translations to people on our platforms, and finally, what the future looks like. So at Facebook, we connect people with different backgrounds and different cultures and that speak different languages. So this means that at some point on your newsfeed, you will probably find some content in a language you don't understand. And in this case, we do want to provide a translation. So first, we run language identification on the content you receive. And in this case, we identify the content as being in French. We also detect the languages that the viewer understands or speaks. So in this case, English and Turkish, but more importantly, not French. So because of this mismatch, we do call our French to English translation system, and we provide a translation, and hopefully a good one. So by doing this, we hope that we've created a more meaningful connection and more meaningful interaction between the viewer and the content. This was an example of one translation, but today, in fact, our backend systems serve almost 6 billion translations per day, and this is happening on 4 different platforms: Facebook, Instagram, Workplace, and Messenger. And in the case of Messenger, this is a very recent feature that was launched this year in May. So I'd like to describe how we use PyTorch and PyTorch Translate to achieve this. So first, we train in PyTorch. Why is that? Because it's easier for faster prototyping, because it's in Python, the API looks like NumPy, and the paradigm is defined by run. And because the paradigm is defined by run, it's much easier to debug. So you can put random PDB or print statements in your code and figure out what is going on with your model computation. And finally, it's much easier for knowledge transfer to have one single framework across our company that every single engineer and scientist can use. So far, it was a little challenging to put these models into production. In fact, this is what the picture looks like in early 2017. We would come up with an idea, implement a model in PyTorch, and then it would take weeks to re-implement that same model in another framework, Caffe2. And the reason it would take weeks is because there were many bugs, and it would take time to squash them all out. Now, thanks to ONNX, which stands for Open Neural Network Exchange Format, the picture looks a little bit better. So it looks more complicated here. We have 3 graphs. However, the important part to remember here is that the 2 steps from PyTorch to ONNX and from ONNX to Caffe2 are now automated, which makes our life much easier. So I'll describe a little bit how this process works. We use neural machine translation. This means that we use these famous sequence-to-sequence with attention models. So it has an encoder and a decoder with attention, and it doesn't really matter whether this is a recurrent network or a transformer network. So the way we do this is we trace the computation for the decoder and the attention, and we obtain a first ONNX representation. We do the same thing for the encoder. Once we have these ONNX representations, we transform them into Caffe2 graphs that we can execute with our Caffe2 executor. And finally, we have some C++ glue code to connect these components together and perform beam search. And the reason it's important to have inference side of things in C++ is that we can integrate with our serving infrastructure in a much easier fashion. So for example, we can take advantage of multi-threading to serve multiple requests in parallel, or multi-threading to serve one request, but faster. So this is actually not enough to reach our latency target, so we need to do a little bit of work on the modeling side. So in natural language processing, it's a well-known fact that the softmax computation is one of the most slowest operations, one of the most expensive ones. And the reason is because it involves a matrix multiplication where the matrix is very big. It involves 100 million parameters. So the first idea to simplify this is to come up with something we call bottleneck layer. So you can go from 100 million to 25 million. But it's still not enough. So the trick here is to, ahead of time, predict what are the likely translation words given a set of source words. And by doing that, you can reduce the number of parameters to around 1 million, which is good enough for our use case. Another very important aspect of reducing latency is to use a custom backend that we called FBGem. So this library will be released open source before December. And it provides us with a 4 times speed up in matrix multiplication when we measure this with a micro benchmark. And in terms of end-to-end latency reduction, it provides us with a 1.3x speed up. This is roughly the current state of PyTorch Translate and what features are important to serve all these translations. So what does the future look like? If you remember, a couple of slides ago, we had 3 graphs, PyTorch to ONNX to Caffe2, but the future is even more seamless. We'll have PyTorch in Python on training side and PyTorch in C++ on the inference side. So for this, 2 things need to happen, at least. First, we need to be able to export the beam search computation directly, and we already have example code in our open source project to do that. And the second thing that needs to happen is that we use the actual PyTorch C++ API instead of the Caffe2 API. And all this work is actually towards our mission of our motto of no language left behind. So currently we support over 4,000 language pairs, but we want to support even more, and of course, we want to improve the translation quality across the board. So feel free to check out the code and the examples that PyTorch translate on GitHub. Thank you very much.
Hey, everyone. My name is Ahmed Ali. I'm a research scientist in the Facebook Conversational AI group. And I'm going to talk to you today about PyText, which is a seamless path from NLP research to production using PyTorch. So let's start with defining what is PyText. So PyText is an NLP modeling framework built on PyTorch for two main goals. These goals, we have heard them a lot during the sessions today. The first is we want to make the research on NLP as easy as possible. So we want our researchers and engineers to experiment with new ideas and approaches, modeling approaches very quickly. And on the same time, we want to allow them, once any of these models have proven value, we want to have a seamless path to production with minimal engineering overhead. The main motivation behind doing that and building PyText is we are an applied research group where we work on a very hot research area. So on one side, we needed to be as close as possible to the NLP community and to run models and experiments fast and try things fast. But on the other side, we are working on products. These products have latency and scale requirements that we need to adhere to. An example of the products that we are working on supporting in PyText is a Messenger M Assistant. So the goal of the M Assistant is to enable users to accomplish tasks faster by showing them suggestions in the conversations. As you can imagine, like in order to models work on in Messenger, they have to be real-time. They have to be designed to scale, because we have a huge scale of Messenger with billions of messages per day. And the third thing is that they need to work on different languages with different modeling needs. Now, let's take an example of a model in M and that we want to improve and see how can we use PyText to improve this model. In this particular case, we want to, M wants to enable the user to book movies faster. And it's doing that. Once it understands the user has the intent of booking a movie, it tries to pop up the Fandango widget here in order to make the movie experience faster for the user. And in order to do that, it first needs to understand that the user has the interest or the intent of buying a movie. And for that, we use a text classifier, a bidirectional LSTM-based text classifier, to detect the intent of the user. And at the same time, we need to get the arguments for this intent. The argument here is a movie name. So in order to show up this widget, we need to know what's the movie name. And for that, we use a sequence tagger, which is tagging each word in the sequence with some tag. And also use the bidirectional LSTM-based. Now, I want to make a couple of iterations of this model or a couple of improvements in order to make the accuracy of this model better. The two things that I want to do is, first, I want, instead of training them in a separate manner, so we have a separate model for intents and separate model for slots, I want to train a joint model for training them jointly. And the reason is to reduce the number of parameters that we are learning, and we better capture the dependencies between the intents and slots. And also, another thing that I want to do is I want to introduce a conditional random field layer, a CRF layer. And for that, we want to add that because CRF has proven that it's better capturing the dependencies between the word tags. Let's see how can PyText help us get this to production. So first, we started with an idea, which is the one that we saw, like the joint training and the CRF. Now, we go to PyText. PyText gives us all the necessary abstractions to write the models, train them, evaluate them, and make it easy for doing any kind of parameter sweeping. It's worth mentioning here that PyText is designed in order to make the model authoring as easy as possible, meaning that if you want to change the model, you don't need to worry about any other thing in the system. All the other components should work out of the box. And you can add a model, and you can expect the trainer and the predictor and all the other components in the system to just work. Once we do all of our parameter sweeping and evaluation, we get a PyTorch model, which can run in Python, in a Python environment. And for that, we have built a Python inference service that the client can talk to. So by doing that, we can have a tiny bit of the traffic, and we can send it to this Python service, and then we can get our online metrics in order to see how good is this model. Once we are happy with these online metrics, we go to the next stage, which is we have the PyTorch model. Now we have the model exporter, which is built on Onyx. As Juan mentioned, this was a work in progress, while PyTorch 1.2 is work in progress. So for now, we still use Onyx. And also, we have all the necessary validations in order to make sure that the PyTorch model is equivalent to the Caffe 2 model. Once we have the Caffe 2 model, now we don't need any Python in the loop. And we can deploy this in a C++ inference service, very optimized for the high load that we are expecting on Messenger. I want to dig a little bit into the model exporter and see what it looks like. So first, what we do is we transform the model from PyTorch to Caffe 2. So now we converted our Python script into a Caffe 2 graph. After that, we do any necessary post-processing on this graph. So that we do two kinds of post-processing. The first one is we prepend any necessary operators for doing numericalizations. So the model expects numbers, but the client is sending strings. So we add the operators to convert that. And also, we add the operators for similarly at the output. So the model output is numbers. The client is expecting the strings. So we do that denumericalization also here. So now we have gone through a full loop of going from an idea to production. Now let's take a more complicated example of a new scenario that we want to support that was not even existed before, that didn't even exist before. So we have we want M assistant to help us with queries or utterances like directions to the Eagles game. So here we have a top intent, which is going to getting directions. But in order to get the location here, there is an implicit intent in place. Because we are not saying the intent, the direction, or the location explicitly. So we need to first have an implicit intent of get event, which is the Eagles game is an event. And from this event, we can get the location. And in order to model this, it's not possible to use the previous model that we had, which is just having flat intents and slots. So we needed to model this as a semantic parsing problem. So the model that we opted for is the RNG, recurrent neural networks grammar for semantic parsing. It's basically used for other parsing tasks. But we used it for this particular semantic parsing task. And actually, we have published a paper. Our group published a paper. And it will appear in EMNLB, the upcoming one this year. And a brief high level of the model is that it's a transition-based parser. It's using a tree, a stack, and a buffer. And it's using LSTM to featurize those. And it keeps track of all the actions that was taken so far, and also as a LSTM. And we have an action classifier on top in order to classify what is the best action to take. As you can imagine from the structure of this model, it's not easy to use Onyx for this. Right? So the issue is that it's very heavy conditional. It has very heavy conditional execution. And the second is it requires a data structure, a custom data structure like stacks here with the Bob and Bush semantics. So the solution for that was using the PyTorch C++ API that Peter just announced. And it might be not very convenient to rewrite a model in C++. But if you look at the interface, you will find it's very, very similar. So you can have the same way of initializing a model, and you can register your model or add a new layers into it very easily. And you can have all the logic that you want, like have conditional execution. You can have custom data structures, and you can have whatever you want using the C++. And you don't need any Python in the loop. Now, after doing that, we were able to run this model, which is very complicated in post-production and even training. We use the same because this is AutoGrad compatible. and we're able to deploy it in production. To summarize, we have built NLP modeling framework on PyTorch to be a single stop for doing quick experiments and to go to production as fast as possible. PyText models right now are supporting very heavy production applications that that are serving billions of queries per day. And our development cycle has improved a lot from like weeks or months to just few days to go from research to production. And just a small announcement, PyText will be open sourced this month, so stay tuned. And thank you from the PyText team, and thank you.
Hello, everyone. My name is Brian Annenberg, and I'm a computer vision engineer working on future-looking technology at Oculus. Today, I'm going to talk about how my team leverages PyTorch to train deep learning models to predict facial expression from audio. Here's a quick video.
This model was trained on PyTorch, translated via Onyx, deployed on Cafe 2 into Spaces to be run with this next-generation avatar.
Este modelo
को PyTorch से ट्रेन किया गया है
durch Onyx übersetzt.
Cafe 2我通じて
et lançado Spaces
pour créer cet avatar
個新一代嘅虛擬頭像。
So why is Oculus interested in facial animation? Well, when you wear a virtual reality headset, you're transported to a virtual world, but you also are able to embody a virtual avatar. With your virtual avatar, you can explore this virtual world and interact with and socialize with your friends and family. We believe that an important part of these social interactions is face-to-face communication, and facial expression is a very important part of this type of communication. Bringing realistic facial expression to virtual reality will significantly improve the quality of social interactions in virtual reality. Specifically, my team at Oculus is working on enabling facial expressivity by improving the audio-based lip sync technology and audio-based event detection, specifically targeting laughter. Lip sync technology aims to animate the mouth given speech. The lip sync mouth can be animated in real time to animate the mouth of your virtual avatar, or it can be applied to animate characters in games or movies. In this image on the right, you see the mouth making different shapes. Each of these shapes corresponds to a sound unit, and the shape is called a viseme. The viseme is the visual representation of that sound unit. Our technology makes use of blend shapes to represent each of these mouth shapes. The blend shapes define the 3D geometry of the mouth shape. For example, there could be a blend shape representing the lips pulled inwards or a lip puckered shape. And our model is capable of predicting a 15-dimensional viseme vector, which is then mapped to these blend shapes, which can then be combined in linear combination to generate any mouth shape. In this slide, you can see a reference image for each of these viseme mouth shapes. So we also developed deep learning models to predict laughter from audio input. This laughter detector is capable of predicting a floating point value between 0 and 1, which reflects the probability of laughter occurring at the current audio frame. The laughter detector is capable of detecting all types of laughs, including chuckles and giggles, for a wide variety of people. In this slide, I'll go over, in a little bit more detail, the network architecture that we use to power both this lip sync technology and also laughter detection. First, we take an audio input, a stream of audio input, take the latest frame, and extract audio features. In particular, we extract 32-dimensional log-mel spectral features. We then make use of a temporal convolution network, a TCN, to predict a 44-dimensional phoneme vector for each audio frame. This phoneme vector is then mapped to a 15-dimensional viseme. In the case of laughter detection, we directly predict the probability score. In this figure, we can see a simplified representation of the model. If we look closer, we see that we're applying convolutions at multiple scales with different filter sizes, for example, 5, 9, 17, which are applied across the temporal domain to aggregate features and build representations at different scales. In this slide, we're going to provide an overview of how we train our model for both lip sync and laughter detection and how we deploy it into product. First, we start off with a large audio dataset of hundreds of hours. Next, we make use of PyTorch's data parallel module to scale the training across multiple GPUs and running on remote Facebook GPU server clusters. We also leverage Facebook's FBlearner machine learning platform to train the model and perform hyperparameter searching. After we arrive at our final model and perform evaluation, we then export this model from PyTorch to Caffe2 CPU-only version, making use of Onyx. We then perform another step in which we convert this Caffe2 model to a fast online cached version called Fast WaveNet, which enables real-time speeds. We then optionally quantize this model so that it can be run on a Hexagon DSP. Running our model on the Hexagon DSP allows us to preserve CPU for other applications and games. Finally, we export the Caffe2 model to protobuffer files, which are integrated into our Oculus Lip Sync C++ SDK, which is then integrated into either Unity or Unreal Engine, such that you can drop this plugin into your application and have real-time lip syncing and laughter detection technology. Finally, PyTorch enabled this project in a variety of ways. The functional style of PyTorch simplified our model architecture while promoting modular code design, which facilitated code reuse. This made it easy to make use of modules across multiple projects and simplified the coding development process. PyTorch also made it very easy to prototype new modules, new layers, and experiment with new operators. Finally, we found that PyTorch made it especially easy to checkpoint and save the model state when training. Also, PyTorch's eager AutoGrad-powered execution enabled efficient prototyping in Jupyter notebooks and debugging in Python with PDB. And finally, the tight integration with the rest of Python data science ecosystem enabled easy experimentation and analysis. So thank you, and please check out and download Oculus Lip Sync SDK from Oculus developers' website.
Hello, I'm Jitendra Malik. I'm here representing Facebook AI Research. And I'm the site lead in Menlo Park. We do work on all areas of intelligence. And I'll show you some of the stuff we have done. So Facebook AI Research does basic research, open research. So everything we do is published. Our code is made open source available. We collaborate with academia. I myself am also appointed at UC Berkeley. Here's an example of one of our accomplishments, Mask RCNN. So as you can see in this image and in the video stream, the various people and objects have been detected and segmented out. And this is amazing. I've been in computer vision for 30 years, and I never thought we could get results of this quality in 2017. But this is the past in some way. What's the future? The future, you can see that we are here just looking at a passive image or a video stream. But when you look in the real world, it's not like that, right? You're a bit confused about what's there. So what you might do is go close to that object, look around it. We are active agents. We move around in the world. We see, we plan our actions, we react to things. That's what we want, embodied intelligence. What does that mean? What that means is that we can no longer stay siloed. This classic style of vision people work on vision, and language people work on language, and robotics people work on robotics, and then we have some learning to glue it all together. That's not enough. We really need to think of intelligence as a process which combines all three of these capabilities. And there are very important questions which lie at the interface. So let's take an example. Visual navigation. How do I go around the world? How do I go around in my house? How do I get to the refrigerator? This is a combination of perception and action, locomotion in a place. More examples. Embodied question answering. I'm in this house, and I have to answer questions like, what color is the car? That requires me to go around, find the garage, find the color of the car. So this is embodied question answering. It's not just from text. It is a body moving around in the real world. More examples. Language grounding. So in tasks such as machine translation, we can convert a sequence of symbols in English to a sequence of symbols in French. But that's not enough, right? We need to know what chair stands for, because you might be able to translate from English to French and have no idea what a chair is in the real world. Language grounding is about questions like that. So all of these require working in the real world. And how are we going to do this? We need to create models of the real world in our systems. So we are going to have simulators of the real world. So we are going to capture the real world. So on the bottom, you see various 3D models and environments. And then we are going to test our ability to perform different kinds of tasks in this environment. So tasks could be navigation, it could be question answering, and so on and so forth. OK, so I'll just pick this as an example, embodied question answering. I'm not going to get into technical details. Here's a paper from various of our colleagues in Facebook AI research, and you can find this if you like. And here's a canonical task they have. So here is this robot. It's somehow put down in some point, place in the environment, and then it's asked a question, what color is the car? So what does it do? It says, I don't know what color is the car, so I'm going to walk around. It opens its eyes, it moves around, and it navigates in the place, needs to have some notion of geography of an apartment, and then it comes to the garage and then says, aha, the answer is orange. So this requires a whole lot of processing. It requires linguistic processing to make sense of the question. It requires visual processing because you are looking at images as you go along. It needs planning and control, and it needs acting in the world. So how are we going to do this? Of course, we're going to use PyTorch, right? So they're going to be so there's going to be a stage which is the visual processing, very naturally done by a convolutional neural network. So that's going to happen. There's going to be processing of the linguistic stream. Well, that requires a recurrent neural network, something like an LSTM. Then there is planning. Planning is stuff like, should I go forward? Should I go turn left, turn right? And then control is the actual action primitives at the level of the robot, which would be, I move 10 centimeters, I again move 10 centimeters, and so on and so forth. So now the architecture, of course, is going to have all these modules, and I'm not going to get into any details here, but these are all available in the paper. And just show you some examples of what one can do. So here's a question. What room is the stereo set located in? So OK, first of all, you suck in the visual stream. So there's some image which is going in through a connet. There's a question which is going in through some recurrent network. And now you issue a series of commands for navigation, and you move around. And aha, here I found the stereo set. Your recognition system says it's a stereo set. You're in a living room. Next example. What color is the sofa in the living room? So you go around, you process the language, you have processed the visual stream, you act in the world, you can answer the question, and so forth. And now, of course, what you saw so far was really kind of, they looked vaguely synthetic, right? So there was a synthetic environment which was being used. But we want to do this for the real world. For this, we are going to build really accurate photorealistic environments of the real world. We need to capture the real world and put it in our computer. Data sets are like so 2010s, so 2000s maybe, or maybe it's like 20th century. The future is environments in which an active agent can move around. And for this, we need to capture the real world, and our colleagues in Oculus, Facebook Reality Labs have developed techniques and scanners which can do a really remarkable job. So we're going to use those to build the synthetic world in which we can operate. What do we get out of this? We are going to get embodied agents. And this is, I think, what artificial intelligence is about. We need to be able to act in the real world. Think of the next generation of agents that assist you. They're not like the old-style agents like Siri, which can answer some questions of databases. They need to help us as we move around and act in the real world. Thank you very much.
Hey, good morning, everyone. Today, I'm going to talk about ELF OpenGo. That's like one of the projects that actually receive a lot of attention about like how the PyTorch can actually be used in different scenarios. So there's one example. So my name is Yuandong Tian. I'm one of the leader scientist engineer of this project. So first of all, I want to talk about what and why we need to do that. Right. So first of all, okay, OpenGo is basically a reproduction of the AlphaGo 0. And people may wonder, like, why we want to reproduce DeepMind's paper. I think there's two purposes. One purpose is that we want to understand why such system actually works and how it works, in which situation it will work better than other situations. Right. And also, FAIR is an open community, and FAIR is very open and want to reproduce results that is very great from the other point of view. So we want to enforce that reproducibility research that others can build upon. So we open source the code as well as the model so that other people can use it. Okay. On the other side, we want to basically build internal reinforcement expertise and code so that we can actually use that for other things as well. Right. So this include distributed training. This include like we're going to improve our ELF platform, etc., and try to apply that to other situations. Okay. So the idea of AlphaGo 0 is actually quite simple. Right. You start from a random model, and you want to train a very strong GoBot without any human knowledge. So at each iteration, and the model is very simple. It's basically like you use the current model. We basically run self-play to generate many games, and then we update the model with these self-play games, and you repeat. Super easy. So to generate a self-play game, basically, you want to use an online planning approach, like many-card tree search, to find the move given the current model. So you start from an empty board, S1, and then you try to expand an adaptive game tree using like 1,600 rollouts to append a move distribution. So once you have this move distribution, you basically sample an action from that move distribution, and you apply that to the current situation to yield the next states. And then you arrive at the final final states where the game's signal is given. You basically know that at the end, you lose or you win a game. So once you have that, you basically collect all the data from each of the situations together, and you train your next model. Super simple. And then the model updated is basically following this objective function. So you want to minimize the distance between the predicted final reward, which is z. So this is the first term, z minus v theta. And you also want to minimize the clear divergence between the many-card tree search policy distribution as well as the predicted policy distribution from your network. And you have additional term that is basically your regularization. Okay. So the network is also a very simple one. You basically use ResNet to predict both the policy as well as the values. Okay. And the input feature does not contain any information about the specific structure of the game, but very raw observations basically the player situations at different time steps. So the method itself, although very simple, is super powerful. It's basically beat the original AlphaGo Lee within 2-3 days. So using like 4.9 games as well as 20 block ResNet. Okay, so this is very, very impressive. And also they have a 40 days version that is even stronger. So since AlphaGo Zero's code is not available and the paper is super simple, and there's a lot of mystery around it. Some people will say, OK, this is basically the ultimate algorithm that can be used to solve everything. And this seems to be like, because it does not use any human knowledge, it seems like it can be applied to any other approaches, any other method, any other issues that you haven't solved with human knowledge. But this is actually not true, because there's any kind of algorithm, there will be a limitation, there will be a weakness. So how can we actually deal with that? How can we understand that better? We're already seeing a few papers from this year's iClear submissions that try to understand AlphaGo Zero. And on the other side, we really want to have a benchmark to have a Ripple implementation to make sure that we understand that using the model that is trained. So we actually want to achieve this kind of goal, so we want to reproduce it. Okay, we use the ELF platform as a basis to reproduce AlphaGo Zero. ELF is our reinforcement learning platform that is published in last year's NIPS as an oral paper. And conceptually, it's actually very simple. You try to make a reinforcement learning as simple as possible by putting all the dirty stuff into the C++ and make sure that on the Python side, it's super simple as a one simple for loop. So in this for loop, every time you try to wait for a batch of games to return, and then after that, you use your PyTorch, favorite PyTorch module to find the action. And you have this action, you send it back to all the previous games. And then the model, the entire procedure continues. So here's like one simple slide summarizing how this ELF platform is working. So we have like a lot of game threads. They all run in C++. And then once you have that, sometimes these game threads want to have neural network support to give back to their action, right? But they want to be grouped together so that the action they return is actually more efficient. Because you know, like in GPU, if you want to run deep learning, it's better to basically batch everything together. So F is basically balance between the throughput between different game threads, and as well as allowing this batching phenomena. So that's basically like one summarization. So we also have a reinforcement learning PyTorch platform that is written within the ELF, and you can write A3C in 30 lines. And this is all powered by PyTorch. So if you want to use it, feel free to use it. And in order to get AlphaGo Zero working, we actually have an extended version of it. It's called distributed ELF. You have one server, and you basically send requests to all the clients. And these clients are playing all the self-plays. And you send all the games back from the clients back to the server so that the server can do this offline training. And the server updates the model from time to time so that the clients can actually continue the self-play with the updated model. So this entire framework basically putting AlphaGo Zero and AlphaZero into the same framework. And you can basically switch between the two modes with a few switches. OK, so we open source the entire system, and we basically get like a lot of attentions. And we also open source the pre-trained model that is trained with 2,000 GPUs in 2 to 3 weeks, and it achieved decent performance against professional players. So this is basically one slide summarizing like our strengths. So we actually collaborate with the Korean Go Association about a friendly game between all the professional players and ELF Open Go. And we invite 4 professional players. They're all on the top 30 level. And each of the players play 5 games against our ELF Open Go. And they all lost. And we actually use only a single GPU to play the game. And I will allow all the premium players to use as much time as possible. So some of the players actually spend 6 hours in this game. And finally, they still lost the game. So this is a very impressive result, I think. So we already open source the code and open source the model, and people can use it. It now becomes, I think, the best open source Go engine in the world. I think everyone is using it. We also compare against another strong board, which is called Lila 0. So this is re-implementation of AlphaGo 0, but using a crowdsourced computational resources. They have trained it for half a year. By the time that we are going to compare with them, so we basically get 980 wins and 18 loss. So the win rate is 98.2. So it's much higher, much stronger than the existing bot. It's also trained without human knowledge. Okay, we got a lot of attentions from people. I mean, after we release the model, from the computer Go server, that is public Go server, that everyone can put bots there. And we see like a lot of bots that has the name ELF, which means that they already use our pre-trained model and try to basically check whether the model is strong or not. We also receive a lot of attention from other people who also work on the same similar projects. And we also put our bots on the Fox server, which is a very famous server on the Chinese forum. So a lot of professional players from China, from Korea, from Japan, they are playing the game against other people, as well as against the bots. And our ELF OpenGo actually received a lot of attention from other people. Yeah, so there's a lot of research findings from this kind of from this kind of practice. There's a few things that I'm basically going to share with you a little bit about that. First of all, we find that, I mean, this is AlphaGo 0 and AlphaZero algorithm. It's actually not a sequential of supervised training. Right? From this diagram, it looks like we collect a lot of self-play games, and then we update the model and repeat. It's actually not the case. It's actually more on the policy value optimization case. It's more on the reinforcement side rather than on the supervised side. Because if you keep your self-play constant, you keep training the model, it will overfit. So you really need to have a lot of data fed into this model so that it will continue updating. So this is actually quite important. And you show that it's actually make us understand the entire system better. Another interesting finding from this implementation is that it's actually improved from the end of the game. So at the beginning, the model is random, and everything is random. How come the model can actually give you something that is useful? It's actually a mystery at the beginning of our implementation. But after we dig deep into the system, we find that, I mean, the system, the algorithm can actually find a direct correlation between the situation that's close to the game end with respect to the final game consequence. And this is very important. Once it finds the direct connections, it will learn to find the good move near the end of the game. And after a while, the good move basically back-propagate or back up all the way to the opening. So after you try to train the model, you realize that the boss actually learned opening at the end. So it's actually already achieved down level, a very strong level, even if the opening does not make much sense. I mean, you will see like random moves at the beginning. You feel like you're going to beat it. But after a while, you find like, oh, its mid-game fighting is super strong, and you cannot beat it. Okay. So another thing issue that we actually find is the stability of the algorithm. I think people in like last year NIPS, they actually criticized the algorithm about the stability. Someone asked, okay, do you have an error curve for your convergence curve? And I think what Dave Silver is saying is, okay, it's too expensive, so we don't have an error bar, which is not a satisfying answer. And we actually do some kind of stability analysis in an involuntary manner because there's a bug in the code. And we actually find this, from this kind of bug, we actually can do some kind of ablation analysis. I mean, there's a lot of interesting observations, and we will be summarizing all of them in the paper, which is still ongoing. And here we summarize some of them. I mean, even if there's no policy head, you can still achieve train a model. And even if there's strong correlation in batch, it still can train. So the system itself is quite stable. Okay. And also, it turned out that Monte Carlo research is super important in this kind of systems. You always will find that the model, if you compare the model with the Monte Carlo research, with the model without Monte Carlo research, it's almost always 99% win rates. So which basically means that the Monte Carlo research actually inject new information to the model via this self-play procedure. So, and basically, the strength of the model is totally dependent on this Monte Carlo tree search as well as capacity of the model. If the model has enough capacity or has limited capacity, at some point, it cannot absorb all the information collected from Monte Carlo tree search or stop training. So if you have a better model or a more capable model, then things will become much stronger. Okay. So, and also, we compare AlphaGo 0 versus Alpha 0. So these two algorithms. The difference between the two is Alpha 0 actually trained the entire model in a continuous fashion. So there's no explicit loop here. So no explicit like stages, right? So you keep generating the data with your most up-to-date model, and you use that data to train your models on the fly. We actually push that to the extreme so that within one self-play, you actually can use 2 different models or 3 different models, depending on like the progress of your update. It turned out that Alpha 0 is much faster than AlphaGo 0. You easily see like Alpha 0 training, the model trained with Alpha 0 is can win like 100 versus 1 against the model trained with AlphaGo 0. So we basically switched to Alpha 0 after a few iterations. So there's other findings in the paper, and we're going to list them in the archive submissions. So I'm not going to develop here about the details. So there's still a lot of other issues in this algorithm. For example, there's a ladder issues. So ladder is one technique that is learned by the human beginners very easily after a few examples, but it's super hard for the computer to learn it. This is because ladder actually involves like a very long sequence of actions. And this sequence of actions is very sensitive to any kind of perturbation. If you make one move wrong, the entire win-loss situation will completely change. So this is actually the weakness part of Monte Carlo tree search, because every time you want to expand your tree, you will have some probability to deviate from your current main variation and try other trials. And this will actually cause problems. So we are still thinking about the new ways to train the model so that it will become faster. OK, so I think I'm going to conclude my talk. There's few future work. For example, we want to work on more research topics to explore using AlphaOpenGo and PyTorch. This includes more efficient training and better reinforcement learning libraries. And maybe in the future, we're going to develop new algorithms that can lead to a better and faster training. Thanks for your attention.
Hi, my name is Dhruv Mahajan, and I'm a research scientist and manager in the Facebook AI. Today, I'm going to talk about exploring the limits of weakly supervised pre-training. To give you some motivation of the problem, at Facebook, the user basically interacts with billions of images and videos every day. Billions of posts are made, image captions are done, which mentions millions of entities as well as concepts which are present in there. This makes it necessary to train us at the scale of billions of images, as well as deal with a very high dimensional label space. Also, to capture the huge diversity of the data at Facebook, we also need to train models which are very high capacity or has a huge number of flops. The main issue with the current image recognition systems is that they rely on manual labeling of thousands of images for each concept. For example, in this case, the annotator will label the image as cat, dog, and that there's a wooden floor. The problem is that extending such an approach to billions of images is completely infeasible. At the other end of the spectrum are the unsupervised approaches, where effectively you're just given a set of unlabeled images without any labels. The issue is that there's a significant degradation in accuracy compared to the unsupervised approaches. The reality, however, lies somewhere in the middle and is called weakly supervised learning. Typically, when you look at the visual data that comes on these platforms, there's a lot of metadata like captions or hashtags associated with this. For example, in this case, a user will tag the image as #cat, or will simply have a caption, a cute cat couple. There's a very concrete information here, like there's a cat present, but also a lot of noise in terms of cute, couple, etc. This type of hashtags can actually provide a very strong supervision for large-scale training. And they also allows us to use the hashtags as they were always intended to. That is, to make the images more accessible to the users. However, such a data has also a lot of associated noise. For example, certain hashtags might not be able to, do not refer actually to the visual concept. In this case, love is a non-visual concept and too abstract to capture. Secondly, a user may have a localized focus on a particular object, in this case, cat, and might not refer all the labels in the scene. For example, he clearly misses a dog here. Finally, the labels might themselves be wrong. In this case, the name of the dog might itself be Husky, and then the user ends up writing Husky, which is definitely not the breed of this dog. What we have done at Facebook is that we have trained our deep learning models using the hashtag supervision at an unprecedented scale of billions of publicly shared images. Our training is done at a scale which is an order of magnitude that has been done anywhere else. We are also able to recognize 17,000 different hashtags, and we leverage the Facebook's distributed training infrastructure to train on massive number of GPUs, and I'll come back to it in a while. We're also able to train our models with much higher capacity than ever before. For example, our biggest model that we trained on is around 850 million parameters. Also, I would like to emphasize that we did not require any complex cleaning procedures to eliminate the noise that is inherent to the hashtag annotations. I'll briefly talk about the distributed training infrastructure that we use for our training. Our models were trained on Caffe2. We had a massive parallelization on 42 8-GPU P100 machines by doing training on around 400 GPUs. Also, to deal with the high-capacity models with millions or hundreds of millions of parameters, we also introduced an efficient memory management for these models. To give you an example of a training, our models, we were able to train on, in 22 days on 3.5 billion unique and 7 billion overall images, a ResNext 101 32x16 model, which has around 200 million parameters. We're also in process of migrating our models to migrating our training framework to PyTorch 1.0. Now let's back to some results. We took over these pre-trained models and then fine-tuned them on various image recognition public benchmarks. The results we actually got were very surprising and beyond our expectations. On the ImageNet 1K, which is by far the most popular benchmark in computer vision, we actually got a state-of-the-art accuracy of 85.4% by training on 3.5 billion training images. The previous state-of-the-art prior to us was 83.1, which means we improved the state-of-the-art by an impressive 2.3%. If we take into account that the architectures here are different and train the model from scratch on ImageNet with the same architecture, we actually get a 6% improvement. We also performed a series of ablations to understand our training and the pre-trained models better. Here, I'm showing the effect of the model capacity. The x-axis shows the number of flops that each model takes, and y-axis shows the ImageNet top 1 accuracy. The gray line shows what happens if you train ImageNet from scratch. Because the amount of data is small, you can clearly see the saturation effect here. The magenta line here shows the effect of our pre-training on 1 billion images on 1.5K hashtags, which have an intersection with the ImageNet labels. You can see a near log linear effect with the saturation in the end that happens because of the saturation in the accuracy. Nevertheless, the slope is still positive, and hence, this means that our models are currently underfitting, and we can even go to higher capacity to get more benefits. Now let's look at the effect of the label space. Here we compare three label spaces with 1 billion training. One is the 1.5K hashtag space related to ImageNet. The second is the 8.5K random hashtags we took. And then third is our full 17K hashtag set. There are some interesting trends here. For example, if you look at this ImageNet 1K target task, you can see that the 1.5K hashtag space does better than the 17K hashtag space. This indicates that the matching the source and target label space actually matters. However, if we take the visually diverse data set like ImageNet 5K or Places 365, the trend gets reversed. Now, the 17K label space does better than the 1.5K label space, which means that we need to increase the visual diversity of the label space also by increasing the number of labels in our training. Next, let's see the effect of data size. Here, the x-axis shows the number of data points in the log scale, and y-axis shows the ImageNet top 1 accuracy. I'm showing this effect for different kinds of pre-trainings done. You can clearly see a approximate log linear behavior, again with the saturation towards the end due to saturation in the accuracy. This training is done with a linear classifier training only, without model fine-tuning, and yet we reach an impressive 83.6% accuracy, even without doing the full fine-tuning of the network. This means that the learned feature representations from this network are extremely strong. Finally, we show the result of transfer learning on different data sets and comparing with the ImageNet pre-training. One can see a massive bump in the accuracies on various data sets. Especially impressive are these curved data set results, where we get a 5% improvement by simply training on 224x224 resolution, whereas to get significant improvements on this data set, one typically has to go to higher resolution or use extra information like pose. Finally, we show the results of fine-tuning on the object detection task. Here, we show that we got relatively smaller gains compared to classification accuracy. This leads us to conclude that there is a possible loss in localization accuracy using the large-scale training, but a huge improvement in the recognition, image recognition task. This is further validated by the fact that if you took a weaker AP at 50 metric, which is more influenced by classification than localization, we do very well there. While on the actual box AP metric, which is more geared towards localization, we do not do so great. This also means that we need to spend more time in coming up with pre-trained models that are more suitable for detection tasks. Finally, to conclude, motivated by our work, there are several directions we are trying to expand it. First of all, we want to train on diverse label set up to 1 million labels, or around 1 million labels, and move towards open word recognition. We also want to extend our work to do weakly supervised video modeling at scale. And we have some initial results here, and they look pretty good. They are very interesting, and please stay tuned for them. We will also like to train on increasing capacities of the models, and there are lots of computation efficiency issues in this case, which we would like to address. Finally, we'd like to scale our training beyond 3.5 billion points to 10 million, 50 billion points. However, to do so, we need to improve our systems further in order to achieve even more parallelization and distribution. I hope you are having a great time here, and thanks for listening to me.
One quick selfie for the crowd before we finish up. All right, how's everyone doing? Everyone hungry? Yeah, okay. All right, so in true SF style, we have food trucks off the grid. So none of this, whatever shit food. Usually at conferences, it's actually really good food. It's food trucks, it's off the grid, and it's actually Chinese donuts as well. So if anyone wants to eat their dessert for lunch, go for it. So they're right out by the registration. So head on out, grab some food, hang out. There's places to kind of chill and whiteboard, and we'll meet back at about 1 o'clock. So thanks.